everyone, this is lecture video 16, and in this lecture we will be dealing with related rights problem, and I will explain this topic through an example. Okay, our first example is here. Let's try to understand. It says water runs into a canonical tank at a rate of 9 feet cube over minute. What does this mean? Okay, in fact, I can draw a water pump here like that. So water is falling into this tank at a rate of 9 feet cube over minute. So this is in fact the amount of water that is being poured in this tank, right? So we can restate this quantity as the rate of change of the volume inside the tank, right? Rate of change of the amount of water. So it is the volume of the water, in fact, volume. So if we denote the volume by V, you can denote it by dV over dt. Remember, the first derivative is the same as the rate of change of the volume here. Okay, then the tank stands point down. The picture is given and has a height of 10 feet, which is put here, and the radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So what does this mean? What do we want to find? How fast is the water level rising, it says. So this corresponds to rate of change of water level. So we start decorating our picture. After some time, there will be some certain amount of water inside the tank. Let's put some unknown variables to our picture. So you will put here this quantity as Y, you will name here as X, you can use any variables you like. And while decorating your picture, you need to be careful about something. If the numbers are not changing, like 10 feet and 5 feet here, you can put those constant numbers to your picture. But the height and the radius of the water inside the tank is changing in time, right? The Y, in fact, is a function of time, and X, which is the radius, is also a function of time. That's why for these two parts, the height and the radius, you cannot insert constant numbers, but you need to name them as variables. Okay, so how fast is the wet water level rising at some particular moment is the question. So this corresponds to the rate of change of the function Y. That's why you can denote it by the first derivative of Y function with respect to t. And you want to find this quantity at some particular moment. You see, when the water is 6 feet deep. This is the particular moment that we are interested. Particular moment, so I will write here, we want to find this quantity at the moment when Y equals 6 feet. And as you notice, I didn't insert 6 feet here as a constant value because it is always changing in time. Instead of writing 6 there, I name it as a function which depends on time. Okay, so after analyzing the problem like that, then you constructing a diagram like what is given and what we want to find. So you can construct such a diagram. This will help you in summarizing the problem. So what is given? We know that, okay, dV over dt is given as 6 feet cube over minute. This is the given information. Sorry, it's 9 feet cube over minute, and we want to find the rate of change of the water level at the moment when Y equals 6 feet. Okay, this is what we want to find. Let's say this is the first step, okay? First step is creating this kind of diagram that summarizes your problem. Second step, okay, by looking at what is given, what you want to find, okay? something about the volume is given, something about the function y is asked, you will try to find a relating equation of these two variables. So find the relating equation. Okay, so how can you relate the volume of the water inside the tank to the height of the water? Okay, so let's say volume of a cone with R is the radius, H is the height. So this volume has this formula, 1/3 pi R square H. Okay, so now you can see how can we relate the volume and the height of the water. So they are related like that, 1/3 pi, 1/3 times pi times radius of the water is X and the height of the water is given as Y according to our picture. And when you find after you find the relating equation, your aim is to eliminate one of the unknowns in your formula. In this form, we have two unknowns, but you need to eliminate one of the unknowns. Then you will look at your picture again. You see there is this similar triangles here, and we will use similarity of triangles to create a relation between X and Y. Okay, let's do that. Similarity of triangles. Okay, then I can write X over 5 is, right? X over 5 is Y over 10. This comes from the similarity of triangles. Then from here, X is solved as Y over 2 after you simplify. You see, X can be written in terms of Y, which eliminates one of the variables here. So the volume formula becomes then Y over 2 squared times Y. Okay, if you do the computation, the volume is given as 1/3 or, okay, let me write the final result, 1/12 pi Y cube. And this will be your relating equation, just like V1. V and Y are related in an equation now. Then the third step starts. Now we will take the derivative of both sides with respect to t, okay? Take the derivative of both sides with respect to t. Why I am doing that? Because look at what is given, what is asked. They are all time derivatives of V and Y. So on the right side, I will have dV over dt. On the right side, 1/12 pi. So according to chain rule, you can derive this. It is 2y squared times dy over dt. And next, you will start inserting the given moment. So now it is time to insert the given quantity, 9 feet cube over minute in your equation. This is given as 9. And okay, you simplify the right-hand side. So you have what? You have 1/4 times pi y squared. What is y at that particular moment that we are interested in? We want to find the result of dy over dt when y is 6 feet. Now you are allowed to insert 6 for y and then dy over dt. This is what we want to find. You see in this equation now, the only unknown is dy over dt, which can be solved as 1/pi feet over minute. So this is how you should treat related rates problems. So if you want to make a quick summary with me, first step is to read the problem, understand it, and create a summarizing diagram like this. What is given and what we want to find. And then you will try to relate the unknown thing to the known things with an equation. So we know some information about the volume. We want to find something about the height. So this is the relating equation of these two quantities. Sometimes it may happen that the relating equation may consist of more than one variable, but no problem, you will search for the ways to eliminate one of the variables. Eliminating here means that trying to write x in terms of y so that you have only one unknown on the right-hand side. Once you handle this, you will take the time derivative of both sides and then you will insert the given information to find the unknown rate of change like that. Okay, so this summary is done here in 6 steps. In fact, we divided into 3 steps, but this is a more detailed box. What we did to solve the previous question, we draw a picture and then we write down the numerical information, this step. And then we write what we want to find. Okay, this part. Next, we create a relating equation. Like here, this equation relates the quantities that we used here. And then we differentiate with respect to t of both sides of that relating equation. And then we insert the given values to our equation and find the unknown rate of change. So let's try to apply those steps once more in this example. What happens here? We have a hot air balloon, which is drawn like this, rising straight up from a level field. This balloon is tracked by a rangefinder 500 feet from the liftoff point. So this is the liftoff point, 500 feet from this point, you have a rangefinder. Okay, you know, this balloon keeps rising straight up like that. So what is the question? At the moment, the rangefinder's elevation angle is pi/4. The angle is increasing at a rate of this much. So what is this numerical quantity here? We will try to express it in terms of the time derivative of something. So this is the rate of change of the angle, you know? As balloon rises straight up, the angle is, this angle theta is always changing. It keeps increasing. That's why it depends on time, okay? The angle theta here depends on time. As time passes, it increases. And that's why you can talk about the time derivative of it. And here it is given that rate of change of that angle is given as this quantity. That's why this can be denoted as the theta over dt. Like that, radians over minute. And this quantity is valid at the particular moment when theta is pi/4, okay? So this happens when theta is pi/4. This is the particular moment that we are interested in. Okay, we are interested in. And then maybe I can also state it like at the moment when, let's write it like at the moment when theta is exactly pi/4. What we want to find, how fast is the balloon rising at that particular moment? How fast is the balloon rising? So how can we write this expression as a time derivative of something? So, you know, we want to find the rate of change of this y quantity. So we denote the height of the balloon as y. So y is always changing in time, you know. That's why we are asking now the rate of change of y. In other words, dy over dt at the moment when theta is pi/4. Okay, so let's start solving the question. We already draw a picture. We understand what is given, what is being asked. So let me write. Given that, we want to find. Okay, the given information is this. At the moment when theta is pi/4, okay? And this is given as 0 times 14 radians over measure, minutes. Sorry. And we want to find dy over dt at the same particular moment. Okay, this is being asked. After doing this summarizing diagram, what is next step? Next step is finding a relating equation of the given quantities, theta and y. Look at your picture, please. How can you relate theta and pi? They can be related through tangent function. So tangent theta is y over, you know, this 500 feet is something constant. It never changes in time. That's why you can insert this constant value to your graph. For example, you cannot insert pi over 4 here for theta because it is changing in time. That's why, okay, 500 feet is here, y is here, tangent theta is y over 500. And then after detecting this relating equation, you can take the time derivative of both sides. This is the next step. Take d over dt of both sides. Okay, for the left-hand side. Tangent theta depends on t. You will start derivating from the most outer function. Okay, let me write. Take time derivative of both sides. Okay, so then what you have, derivative of tangent is secant square. You don't touch inside, and then you need to multiply with the derivative of the insider part, d theta over dt. Here, 1 over 500 is just a constant in front, and then dy over dt. Okay, now we are ready to insert the given moment. Okay, so we are interested in this particular moment when theta is pi over 4. So what we have, secant square of pi over 4 times d theta over dt at this particular moment is given as 0.14. Okay, 1 over 500 is there, and this is what we want to find, which is the only unknown in this last line now. What is secant square pi over 4? Okay, let's handle it here. Secant square pi over 4 is 1 over cosine square pi over 4. Okay, and cosine square of 45 degrees is what? It is 1 over 2. That's why this is computed as 2. So let's insert it. This is 2 times like that, maybe, okay. I should keep writing that like this. 1 over 500 dy over dt. From this line, you can solve the only unknown dy over dt at the moment when theta is pi over 4. The result is 140 feet over minute. Okay, so what I did at this step is I'm inserting at this particular moment when theta is pi over 4. Okay, so this is the result, and let's go over the steps that we follow. We summarize the problem, writing what is given, what is asked. We find the relating equation of the variables that we write here in the previous step, and then we take the time derivative of both sides, and then this can be counted as the last step, and then we insert the particular moment to solve for the only unknown. Okay, let's move on. This will be the last problem in this lecture video. There is a sliding ladder here. A 13-feet ladder is leaning against a house. When its base starts to slide away, okay, this is the base, and it starts to slide away towards this direction. by the time the base is 12 feet from the house, the base is moving at a rate of 5 feet over second. Okay, so for this question, I will construct the general structure for you and you will try to solve it by yourself. Okay, so what is given here? Let's write given that and want to find. What is given? The base is moving at a rate of 5 feet over second. But this is the rate of change of what? You know, this length is denoted by X and this length is denoted by Y. As the ladder slides towards this direction, the base, you can see that Y and X are both functions of time. They are changing in time. And this given quantity is in fact dx over dy, right? The dx over dt. Rate of change of x with respect to time is given as 5 feet over second. And this happens when the base is 12 feet. So when x is 12 feet, the rate of change is given like that. So part A, the rate of change of the base is given at the moment when the base is 12 feet. This is given as 5 feet over second. And in part A, what we want to find, how fast is the top of the ladder sliding down the wall at this particular moment. So this time we wonder the rate of change of y at the same particular moment. This is what is given and what we want to find. Step 1 handled. Step 2, we need to find a relating equation. How do you relate x and y? By the way, since the length of the ladder is fixed, it is not changing in time, you can safely insert 12 for this quantity. And the relating equation will come from the Pythagorean identity, which is well known by all of you, right? 13 square. And now next step is take the time derivative of both sides. Take d over dt of both sides. So what you obtain then, x and y depends on t. We are taking the time derivative using chain rule, of course. 2x times dx over dt plus 2y times dy over dt. And on the right side, you have a constant. That's why the derivative of that constant is just 0. Okay, now it is time to insert the given known values to your equation. At the moment, when x is 12, dx, okay, so let's try to insert this particular moment. I will be inserting here x as 12, 2 times 12 times, and this becomes at this particular moment, it is given as 5 plus 2 times. This is what we want to find. And there is also y here. What is y at this particular moment? And you know, you can easily use this equation to solve for y at when x equals 12, you know. Y square is 13 square. From here, y becomes 5. So that's why you need to insert 5 for y and dy over dt is 0. In this line, the only unknown is dy over dt, and you can easily solve for it as, so let me see, these are gone, this is gone with this. So it is, I guess, minus 12 feet over second. So this is our result. and we obtain minus, you know. And it is totally acceptable here. We expect that we will find a negative value because, you know, here, we are talking about the rate of change of y function, and in fact, it is decreasing. So we expect to find a negative value for dy over dt, right? That's why everything makes sense. And this shows that y is decreasing. Okay, I stop here. Thank you for your attention.